4. The Poisson distribution. The Poisson distribution is useful for considering the distribution of random events. Poisson probabilities are used for data that arise from the number of occurrences of an event per unit time or space. Example, the number of E cells per cm square on a microscope slide. Named after the French mathematician Simon Poisson, it is also used as an approximation to the binomial distribution. Conditions for a Poisson distribution. X has a Poisson distribution if X is the random variable, the number of occurrences of an event in a given interval of time or space, such that 1. The event occurs independently, that is, the occurrence of any event in a particular interval of time or space does not influence the occurrence of the event in any other disjoint interval of time or space. 2. The event occurs uniformly, that is, the expected number of events or mean in a given interval of time or space is proportionally to the size of the interval of time or space. 3. The chances of 2 or more occurrences in a short time interval or region is negligible. Examples of events which follow Poisson distribution. Example: A. The number of floors in a given length of material. B. The number of car accidents on a particular stretch of road in one day. C. The number of telephone calls made to a switchboard in a given minute. And D. The particles emitted by radioactive source in a given time. E. The number of sandstorms occurring in a given period of time. Note that all these examples have space and time. 4.1 Definition. If X is a random variable, the number of occurrences of an event in a given time interval or space, then X is said to have a Poisson distribution with parameters lambda. In short, X follows a Poisson, notation is PO, bracket lambda. The probability distribution of X is as follows. Probability of X equals to X is equals to e to the power minus lambda times lambda to the power of X divided by X factorial, where X is positive and X takes the value from 0, 1, 2 and so on. Example 12. The number of times a radio set breaks down in a year, 52 weeks, may be taken to be a Poisson variable with mean 1. Calculate A. The probability that a radio set will break down more than twice in a year. 2. The probability that a radio set will go for at least 3 years without breaking down. C. The probability that a radio set will break down twice in one particular week. Take note of A, B and C where the time frame is different. A. Let X be the random variable, the number of times a radio breaks down in a year. So, X follows a Poisson 1. Since the question asking for more than twice, it means probability of X more than 2. And GC cannot compute more than. You have to convert it into less than, as 1 minus P, X less than equals to 2. And using GC, you have the value 0.0803. And the command of GC is as shown. Taking note that because of inequality, you have to call for Poisson CDF. And the screenshot is as shown. B. Let us define Y to be the random variable, the number of times a radio set breaks down in 3 years, taking note that the interval has changed. So we need to work out the corresponding lambda. Therefore, y follows a Poisson 1 times 3, and y now follows Poisson with lambda 3. And the question is asking you without breaking down means probability of y equals to 0, and that will give you 0.0498 as shown in the screenshot. C. Let us define W to be the random variable, the number of times a radio set breaks down in 1 week. C, take note that the time frame has changed to week. So W follows a Poisson as 1 over 52. The question is asking you for twice, therefore P probability is W equals to 2, and that corresponds to 0.000181.